so how do you actually do this, right? If you want to actually build a machine like the VAX, it's a little like Minecraft, right? So, like if you want to build computer chips, right? There's software to do that. We're going to start talking about Verilog. Well, you can write Verilog code to describe a computer chip, and you hit the button, and it makes the file that you send to the chip manufacturer, and they make chips for you, right? It's very, very painless compared to how it used to be, which was, well, you're trying to make a little tiny chip with, you know, transistors and wires and resistors. And how do you do that? Well, you push all the tables together, and you get a big piece of transparent plastic, right? And you get really fine pens, and you get a good straight edge, and you draw what you want your circuit to look like, where the wires are, where the transistors are. You're not drawing a schematic, you're actually drawing the things that will turn into wires or pieces of polysilicon or pieces of diffusion layer or connections between layers, but you do it on this big sheet of plastic, right, 20 feet across. You can find pictures of people crawling around on this thing, sketching with these tiny pens, right? And then you take that and you basically use a lens to reduce it optically. And you shrink it down to, you know, the size that you want. And you use that to hit photosensitive chemicals that will be changed by the presence of light or the absence of light. So now you shine light through this and you hit something that's been treated with these chemicals, and wherever there's a solid line drawn up here, it changes the material properties on that piece of this substrate so that it's resistant to a certain chemical. And where light goes through, you get pieces that are not resistant to that chemical. So you expose it to this light, you stick that thing in this chemical, and wherever you had a solid line, the material persists. Where you didn't have a solid line, the material gets dissolved away. And now you've just etched a pattern of metal that matches where you had drawn lines indicating you wanted metal. And now you get another big sheet, and you draw your next layer, and you use a different set of chemicals, and so on. And you build it up piece by piece. Okay, so just like in this course, right, to build your traffic light controller, you got to get parts, you got to get wires, you got to get a breadboard, you got to start putting things in holes and jumping things over and so on and so forth. But first you had to come up with the truth tables and turn those into equations and then simplify them with K-maps, yada yada, right? But all that stuff can be automated. Okay, and today most of the design work that we do is automated through a series of tools. So what we're going to be talking about for probably the rest of this term is hardware definition languages. Just called HDLs. Not the cholesterol kind. So HDLs are ways that we can describe circuitry, and we're going to write files that look very much like computer programs. We're going to have declarations, we're going to have, you know, I equals I plus 1, we're going to have if statements and switch statements and for statements and things like that. And it's going to look a lot like writing a computer program. Okay, so here's the most important thing that I'm going to tell you about hardware definition languages. This took me like 3 years to figure out myself once I started trying to learn HDLs. It was about 3 years before this finally clicked for me. When we write, so the language we're using is Verilog. It's just a version of an HDL. There's Verilog and there's VHDL. Those are the two main languages. Verilog seems to be more popular. It's less quirky in a lot of ways. So the most important thing to keep in mind when writing Verilog, you are not writing a program. It's going to look like a program. If you've done programming, that's going to hurt you because you're going to think that you're writing a program, but you're not writing a program. We are not writing an algorithm which says do this, do that, check if this is true, and now either go and do these things or do those things. That's not what's going on in Verilog. When you write something in Verilog, what you're doing is you are describing a piece of hardware. and it's a huge difference. And if you completely ignore that difference, sometimes it doesn't matter. You can think that you're writing a program and hey, you finish your code and it works great, right? But when it gets really tricky and it's not working at all and it's not making sense and it's really confusing, there's a good chance it's because you're switching those two things with each other. Writing a program to implement an algorithm versus describing a piece of hardware. Okay, everything we do in Verilog is basically describing a piece of hardware. And that will come back to that when things start looking really like this isn't making any sense. I don't know what I'm doing here. I don't get it. I'd come back to this and see if that helps. It's a piece of hardware, not a program. All right, so let's look at some resources. So there's stuff, I don't know if I've made it available yet or not. Let's find out. All right, so there is an introduction to Verilog posted along with important Lab 7 notes. We're not going to start Lab 7 yet. We'll talk about it Thursday. So this is available. This is the latest version of a short intro to Verilog. I wrote this about a year ago. The intro is kind of what we already said. All right, so let's talk about a few things. There's Verilog, which we're going to talk about right now. And then there's software tools that work with Verilog that will let us do things like take a Verilog description of a circuit and somehow actually build that circuit. I'm not going to get into the software today. Okay, this tutorial gets you through some of that. The important notes on Lab 7 gets you more into looking at some of the software. But I want to just talk about Verilog for like the next half hour as a language itself. And then we'll start playing with tools on Thursday. And I'm also going to give you an optional Lab 8. And I don't know how much it's going to be worth. But optional Lab 8 will let you actually use Verilog to actually tailor a piece of physical hardware using a Verilog description. And I got to figure out what I want that piece of hardware to do. But most of what we're going to do for Verilog is playing with simulation. So you can write your Verilog description, you can run it through a simulator, and it will show you what your circuit did. You can say, I want to feed in ones and zeros like this, and it'll figure out what the outputs are. But then optional Lab 8 will actually be able to take a piece of hardware and implement your circuit on it. So we'll talk about that on Thursday also. Okay, so the circuits that we're describing are built around the idea of a module. A module is just kind of like a single entity, kind of like a function in programming languages. Okay, it's not a programming language. It's a single block. So if you wanted to build something that does an exclusive OR, you might make a module called my exclusive OR, right? And it would have two inputs and an output. And you would write Verilog code that says here's what the output should be based on the inputs. Okay, the syntax of Verilog is potentially really annoying. You need a semicolon after almost everything. But there's a few places where if you put a semicolon, it'll complain. So it's got some quirks. And I think I've gotten rid of the typos in this document. So you can use this for like samples of code. And if you're not sure where semicolons go, come back here. But there's probably still some typos, so let me know when you find those. Okay, so here's the definition of a module called mod name with three things, arguments, A, B, X. A and B are inputs, and X is an output. Okay, I've just described a system diagram. Right, I'm creating something called mod name. with two inputs A and B and an output X. Right? I've just described this. I haven't said anything about what happens inside here, about how A and B are used and what determines the value of X. But I very clearly said this is something called mod name. It has two inputs called A and B. It has an output called X. So that's the system diagram. That's what we start with, right? First thing you do in a design process. And so that comes up by saying mod name and then listing the inputs and the outputs. And don't worry too much about the wire statement yet. But to begin with, everything's going to be a wire, which just means it's a wire. Right? So it's something you put in your proto board, it goes to A and B and comes out from X. And then the famous miscellaneous statements, right? And then the keyword end module, and this is where you cannot have a semicolon at the end, or it'll yell at you. I don't know why. Okay, so that's a very basic module. It does nothing, right? We haven't said anything about A, B, and X. But that's sort of the outer block. That's what I just said. Okay. So you can put comments in Verilog, and I strongly recommend getting in that habit, right? And if you're doing 224 with me next fall, you're really going to want to get good at making comments. So you can do comments like you do them in C. You can say /*, put in a bunch of comments, and then a */ at the end. So you can have multiple lines. Or you can just say // and everything on that line becomes a comment. If you do /*, don't forget to do the */ at the end. If you forget that, your entire thing is one big long comment and you keep trying to run it and it doesn't do anything and you're going to drive yourself crazy. You're going to keep changing the code and still not doing anything, still not doing anything, and about 5 hours later you'll be like, oh, it's all a comment. Okay? So I usually use a // because this only goes out for one line. All right, so you can put comments in here, and comments are useful for you. They're not used by the software, but they're for your benefit, right? So what are A and B? Oh, A and B are the two button inputs. Oh yeah, I'm gonna have push buttons. And X is high when A equals B, otherwise X is low. Okay, now I know what I was doing with this, right? Verilog is case sensitive like most modern things. Right, C, Java, all this stuff, uppercase, lowercase, totally different. So be careful with that. All right, well, we can define combinational circuits, right? So this is first half of 250. So here's a module I'm calling my and. It has 4 parameters, A, B, C, X. A, B, C are inputs, X is the output. And I have one miscellaneous statement in here which says assign X equals A, ampersand B, ampersand C. Ampersand is interpreted as a logical AND. So this is saying X should be set equal to the logical AND of A, B, and C. And the assign statement is important. If I just say X equals A ampersand B ampersand C, it's not going to really know what I want. When I say assign something equals something else, I'm saying I want to take a wire and connect it between, in this case, X and that AND operation. So this is a really short Verilog program, but it's a powerful one. So let me draw a system diagram. So 3 inputs A, B, C, output X. So this assign statement says the following. Let's take A, B, C, let's AND them together. Well, how do you build hardware to do a logical AND of two things? You make an AND gate and you feed the two things into the input. And it actually understands that I'm trying to AND 3 things here, so we'll actually configure a 3-input AND gate. So here's the circuit that it might be building, right? 3 inputs A, B, C, they're connected to the input of an AND gate. Here's some wire connected to X. This assign statement says, take the thing on the right, which is A ANDed with B ANDed with C, connect a wire between that and the thing on the left, which is X. So when you say assign X equals A and B and C, that says, put a wire here. So I've just defined a module called myAND, which acts like a 3-input AND gate. And it almost couldn't be simpler. And if you want to do an OR, you can do a pipe. If you want to do a NOT, you can use an exclamation mark. Let's see if I have any code down here. So there's a pipe for an OR. I don't have exclamation marks. So suppose I wanted X to be AB or BC. Right? I could say assign X equals A and B or B and C. And the software will do something to create a 2-input AND gate, another 2-input AND gate, feed A and B to the first, B and C to the second, take their outputs, feed it to a 2-input OR gate, take the output of that OR gate, connect it to X. So building circuits just got a lot easier. Now in simulation, right, I could run a simulator and I could say, okay, go through all the possible combinations of A, B, and C and show me what the output for X is. And it will generate timing diagrams. Here's A doing this thing, here's B doing this, and C doing that, and here's what X does in response. And you can use that to verify the behavior of your circuit. But with physical hardware, I can go through more software and I can say, take this Verilog output and actually program this chip to implement this circuit that I've described. And I can say, let's use pin 17 for A and pin 39 for B and pin 64 for C and pin 12 for X. And I program this chip, and now I can take this chip off, I can connect it to a breadboard, and if I put 3 switches onto whatever those 3 pins there were that I named, and an LED on pin 12 for the output, it's a 3-input AND gate, right? Or, you know, AB or BC, or whatever I wrote the Verilog for. So it's customizable hardware. And more, this is how circuit design is done, right? It's using Verilog to design the circuit and then using something like programmable logic to actually implement it. The programmable logic is nice because if I really wanted A, B, or B, not C, right? Well, if I take my Verilog and I send it to a chip manufacturer and they make a chip for me, and I test it and it's not working, and I go through my code and I debug and I say, oh yeah, I really meant B ANDed with C bar, I just wasted a few $1 million. Right? Because that first chip you get from a chip manufacturer is millions of dollars for one chip. Now if I want to make a second chip, it's really cheap. It's just a copy of the first one, but making that first one is really expensive. And you got one wire in the wrong spot, you got one place you meant OR and you said AND, throw it in the garbage, grab another few $1 million, try again. Right? It's a really, really expensive development process. And about 10 years ago, it started to lead to some brain lock in the valley because people were so terrified of making mistakes. Because they knew, like, if this isn't absolutely perfect, it's going to cost my company a few $1 million. You know, what's that going to do to my job? What's that going to do to my bonus? And it was getting really hard to get people to sign off on designs. It's like, well, you test it and sign off on it, you know. No, you test it. Right? So programmable logic, we don't have to worry about that. Because if you mess up, change your code, hit the program button, a minute later, you got your chip reprogrammed. And you can do this more or less, you know, as many times as you can flash a flash drive. It's more or less infinite use. So this is a really sweet design process to get fluent in. Okay, so how many people here know C? I know you're taking 121. Do you remember the ternary operator?
Oh wait, is that? Oh wait a minute. Oh, that.
Something like that. So this is just a fancy way of saying if A equals B, set X equal to 10, else set X equal to 15. And more generally, we could say something like X equals some condition, V1 colon V2. So if this condition is true, set X equal to V1, else set X equal to V2. So in C, you can just write an if statement, right? And it's almost always as easy. In Verilog, we can actually use this ternary operator, this question mark, in an assign statement, which means we can squeeze these if-then statements into a single assign. Let me see if I have a good mux example. I'll just make one up. Okay, so let's make a circuit. Here's I1, or here's I0, here's I1. Here's select. Here's out. And this is a 2-to-1 multiplexer. Multiplexers are the key to life, right? So this is a multiplexer. And you can build big multiplexers from little multiplexers. So this is a good circuit to be able to build. So remember what a multiplexer does?
Selects an input.
Selects an input. If select is 0, it's going to take I0, send that to the output. If select is 1, it's going to take I1, send it to the output. So it's a steering network. It basically chooses which of these inputs to send to the output. And we can write a truth table for that, and we can write equations, and we could simplify them, and then we could do an assign statement, out equals I0 bar and select or blah, 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 right? But we can take advantage of this ternary operator, and we could do something like this. Assign out equals select equals 1, I1 colon I0. And logically this says if select is equal to 1, set out equal to I1. Otherwise, assign out equal to I0. So it's kind of like it's building a wire between one of these or the others based on the select value. But you can't build a circuit where the wires appear or disappear based on the value of an input. I mean, you can, but we don't. So this actually gets implemented with this, right? In fact, any time that you use this ternary operator, you're asking Verilog to synthesize a mux for you, right? And it'll build a mux to perform that operation. So this starts moving us towards a theme, which is, even though you can do gate level design in Verilog, even though we can say give me a 2-input AND gate and a 2-input XOR and a 3-input OR and connect this to that and this to the other thing, the real power of Verilog is you can tell it what you want your circuit to do, and it'll figure out what the circuit should look like. As opposed to saying, here's what my circuit should look like. It should have 2 AND gates and a connection from here to there and so on. It's nice when you tell Verilog, what do I want my circuit to do? And let the software figure out how to make the circuit to do that. And we're going to take that to an extreme over the next few classes. To the point where we can design a state machine and basically just describe if you're in this state and this is your input, set your output to that and go to that state. And we can just write statements that basically say those things and it will figure out how to make that happen. There's also state machine specific tools available where you can do something like just draw a state diagram and it'll build a machine for you. It'll even neaten up your drawing for you if you like. You can say make it pretty and it'll like put everything where it should so the arrows aren't crossing too much and so on. And there's a checkbox for full encoding, there's a checkbox for one-hop encoding, there's a selection box for what kind of flip-flops do you want to use and so on and so forth. Alright, so combinational circuits. And you should look through this document on your own. I'm not going to go through all of this, and I'm certainly not going to read it to you. But you should go through it. The section on instantiation in particular, I'm not going to go into the details of right now, but the basic idea is we can have something like subroutines or functions, right? Since we're describing a module, we could make a module which implements a multiplexer. We could take a module which implements a 4-bit adder, and we could connect those together and make a new module which uses this multiplexer's output to feed this input of this adder, and so on. And so you can build blocks of circuitry and connect those together to make bigger blocks and connect those together to make bigger blocks. Right? Now that's still kind of descriptive Verilog. That's describing your circuit. And there's times when that's what you want to do, as opposed to trying to describe the behavior of your circuit. But maybe it's a combination, right? Maybe I'm describing the behavior of this arithmetic unit, this thing that can add or subtract or do logical operations. But now I want to connect that to some other piece of circuit in a particular way. And it might use a description of the circuitry like that. So that's what this section on instantiation is. And basically, I'm saying here's a module called mySelect. This is a 2-to-1 multiplexer, right? There's our assignment statement. And here's my main module, and I'm saying I want a multiplexer that I'm going to call U1. This is what the two inputs come from. This is what the select comes from. This is where the output goes. And I'm using this U1, right? This mySelect inside this other module. Right, that's the same U1 when you label your components on your circuit diagram. Okay, and there's syntax details on here. If you want to write a value in binary, you can do it by saying something like 8 single quote B, and then you can list 8 bits. And it'll understand that's a binary number. Or you could say hexadecimal numbers, and so on and so forth. And this is your first course with me for most of you, but by the time you're done taking courses with me, you'll have heard this a number of times, right? Verilog is like this, right? And the part of Verilog I'm talking about is like this, okay? It's a huge, huge thing. Huge language with lots of features and lots of keywords and things like that. And most of it I'm not going to go into. Okay, because if you understand Verilog, if you understand the basic ideas of it, if you understand that it's describing a circuit instead of being a programming language, and you understand a few fundamental concepts, you can pick up all those other things really easily. Okay, same thing when I teach Unix, right? Unix is this, I teach this, right? But the 7 or 8 things that I teach you will be enough to do anything that these other things can do. It's just going to take more steps maybe, right? And eventually you get tired of doing the same 6 steps every time you want to do something, so you do some looking around. You say, oh, there's another command that'll do that in 1 step, and you add that to your toolbox, right? But my goal here is to get you sort of the essential kernel of Verilog that lets you do all the things we need to do and gets you more familiar with the underlying concepts, so that if you want to, you know, learn about some new statement or some new way to express numbers or something like that, it's easy for you to take this and build on it. Okay, so the real power of Verilog is what I call behavioral Verilog, describing the behavior of your circuit. What you want it to do, instead of saying this is what the circuit should look like, say this is how the circuit should act. So here's a classic example of behavioral Verilog. We want to know if two inputs are equal. So I use my ternary operator and I say, let's assign the output x here so that if A and B are equal, the output's 1. Otherwise, the output's going to be 0. And now I can feed in my two inputs A, B, and the output of the circuit will be a 1 or a 0. Well, we could do that in the collaboratorium, right? We could write a truth table for this, and it's pretty easy. Here's A, here's B. Here's our equal output. And it looks like that. And so it's just A bar, B bar, or AB. It's also an exclusive NOR. So this may not necessarily be easier than just saying x equals, the negation of A, x or B. But suppose A and B were 32-bit numbers, and I wanted to make a circuit that would tell me if those 32-bit numbers were the same. I could have 32 exclusive NORs, and I could take all those outputs and AND them together. And if it's a 1, then all 32 bits were the same. Or I could write exactly the same one line of Verilog. Assign x equals. And if I tell it A and B are 32-bit inputs, that assign statement still works. Or maybe I want to know if A is bigger than B. I can change that equal sign to a greater than sign, and I've got a circuit. How do you build a circuit by hand that tells whether this 32-bit number is bigger than that 32-bit number? That's a hard circuit to design. Because you have to basically start from the most significant bit, find the first place where the numbers differ, and then based on the sense of the difference, you set your output accordingly. That's a big circuit. Right, it's still one sentence in Verilog. So this is what I mean by behavioral Verilog, right? This is what I want it to do, and I let the software figure out what the actual circuitry looks like. How about a 2-bit adder? Assign S equals A plus B, semicolon, you're done. There's your 2-bit adder. So you can see where this could be useful, right? It knows how to do addition. If you're implementing this on a piece of hardware that has an actual adder unit, it'll use that. But if you don't, if you just run this through a straight Verilog compiler, you'll come up with a circuit that has a bunch of ANDs and ORs and XORs, and maybe does a full adder, half adder implementation. If the Verilog compiler was smart, and you put in 2 bits for A and B, and you get out 3 bits for S. And much less chance of making a typo when this is how you define your adder. And then if you want to use that in something else, right, you just wrap something else around that and you keep building. So questions or comments or thoughts up to here? Because I'm not going to go on to event-based behavior. I'm going to call it quits at this. And Thursday I want to start looking at some of the actual software and get us up to speed on that. And then we'll start talking about sequential circuits, which is event-based behavior. So that's where we'll start having things with a clock. But I've already blown through like a week's worth of Verilog. So any questions up to here? So Lab 7 is a software lab, and you can do it in the collaboratorium or you can do it on your own equipment if you want, but there's not going to be anything to physically build for Lab 7. So you can still do this in groups, right? But as usual, you want to make sure that everybody who's working out in the group is actually, understanding what you're doing and so on. And then that'll be a software lab, basically. All right, I will let you 2 minutes early, and I will see you on Thursday.